Hello, in the lecture 47 we studied the design of chute spillway principle. Now we are going to solve some design problems so that you understand how to design the chute spillway. So, this lecture is again divided into two parts, that is part 1 and then part 2, and now we are going to start the part 1 design problem. So, chute spillway design part 1. Now, coming to the problem, in the first what are the dimension given? The spillway crest level is 200 meter and the level of bottom flank at which low ogee weir is to be constructed is 192 meter. Design discharge is 5000 cumex. Downstream tailwater corresponding to this discharge is 103 meter. The spillway length consists of 5 span of 10 meter clear width and the thickness of each spillway is to be assumed 3 meter, and assume if there is any data needed. So, first we go for the discharge and we go for the trial and error method here first and see how our assumption is correct or not, and if it does not follow the correct assumption, then we have to redesign our problem. So, first we calculate the design of the approach channel. So, the first component of the chute spillway. So, we first calculate the Q using this equation. So, HE is the height, total height, that combination of design height as well as the velocity of approach, and assuming the coefficient of discharge as 2.18 and taking LE as the clear width, which is again an approximate. So, LE as given in the data, we have a 10 meter span, the spillway span of 5 spans are located here. So, 10 meter of each width and the 5 spans. So, this come out to be 10 multiplied by 5. So, 50 meter that we are going to plug here, and C is the coefficient of discharge, and in that way after plugging this one to equation 1 we have H as 12.58 meter. So, this is the H is the upstream level is designed here. Now, the upstream water level, this one is a combination of the crest level plus H. So, the crest level is given in the problem as 200 meter, the spillway crest level which is located here. So, 200 meter plus our calculated height, now it comes out to be 212.8. Now, bed level of river in a flank, it is given as 192 meter in the problem. The level of bottom flank at which low ogee weir is to be constructed is 192 meter. So, we plug it here. So, total water depth, what will be it is? This is the subtraction of the upstream water level minus the bed level in the river flank. So, which comes out to be 20.8 meter. Now, we assume that the channel is 1:1 of the side slope. Now, the width of the channel B is total length of the spillway, that is 50 meter, and since we assumed it as a trapezoidal. So, 50 plus 4 into 3. So, 1:1 slope. So, it is the total width of the channel is if we assume it is as a plane. So, it is a trapezoidal channel. So, we have this. So, this is the 50 meter and 1:1 slope. So, we calculate this as 50 plus 4 into 3 62 meter. Now, coming to the area of the channel, it is a B plus y into the depth of the y thickness here. So, it comes out to be 1720 square meter is the area. So, this is the total dimension of the channel. Now, coming to the velocity of approach, which is Q, the discharge divided by the area, total area of the channel. So, since the discharge is given in the problem as 5000 cumex and the calculated area is 1720 square meter, we divide this and we get the velocity of approach, which comes out to be 2.9 meter per second. Now, the velocity head is v square upon 2 g, which is again a calculation from the kinetic head. So, this is now comes out to be 0.43 meter. So, once we have this, we calculate the weighted perimeter of the channel. So, this is the velocity head here 0.43 meter, and now coming to the calculation of weighted perimeter, since we assume that channel as the trapezoidal. So, it is the formula is B plus two root 2 d, where is d is the water depth. So, B is the thickness of the channel that we calculated in previous step in 2 root 2 and 2 d that we calculated earlier. So, the depth of water is coming out to be here in calculation of the weighted perimeter. So, the weighted perimeter of the channel comes out to be 120.8 meter. Now, we plug this into equation of hydraulic radius. So, since it is trapezoidal channel, so R equal to A upon P. So, this comes out to be 14.2 meter. So, this is the hydraulic radius. And now, we calculate the frictional head. So, assuming the length of the channel as 160 meter, the head loss due to friction up to the spillway crest is given by the Manning's formula. So, the head loss is calculated using the Manning's formula that we also studied in the spillway design. So, here we use the equation So, here the S comes from the Manning's formula. So, this one, after plugging this, we comes the equation reduced to this form, and here we calculate the HF, the head loss due to friction, where we assume the Manning's roughness coefficient as 0.019, which is an approximation or the value for a natural bed channel. Now, the level of upstream water level. So, upstream water level plus the velocity head minus head lost up to the spillway crest. So, here the upstream water level was calculated as 212.8 and velocity head we calculate as 0.43 and head loss due to friction was 0.016 that we calculate here, and that comes out to be 213.2 meter. Hence, the head over the crest including the velocity of approach is 213.2 minus 200 meter, which is given in the problem, that is spillway crest level, if you remember. So, this comes out to be HE as 13.21 meter. And now, the HD is a combination of HA and HE. So, HE is a summation of HA plus HD. So, from that we can calculate the value of HD as HE minus HA. So, that comes out to be 12.78 meter. Now, we have to correct the coefficient of discharge. So, how we calculate coefficient of discharge? So, there will be correction in number of way. So, correction due to the height of the weir. So, this kind of graph is always given with along with the design problem. So, h upon h d is now we calculated h as 8 meter is given in the problem. And h d we calculated as 12.78. So, it comes out to be 0.63, and h e upon h d is again we calculate as 1.03. So, now we have the ratio between h e by h d, which is 1.03 here. So, if we click our pen here and we take the value here upon the C by C d, we find that C by C d is comes out to be 0.98. So, here is the value. Now, we correct for h upon h d, this is given, and this is the corresponding slope at 1:1. We assume the trapezoidal channel with 1:1 slope, and the corresponding correction factor comes out to be 1.008. Now, the total correction factor is now combination of C is 2.2 multiplied by 0.98 and then 1.008. So, the value of correction factor comes out to be 2.17. Now, coming to the effective length of the spillway crest. So, so we use this equation here. Now, we go for the calculation of LE. So, we assume that Kp as 0.01 and Ka as 0.1. So, now we calculate the LE as this is the 50 meter, and we plug this in the equation, and LE comes out to be 46.3 meter. Now, the correct head will HE is given by following equation. So, we plug everything back in the equation of discharge, that is Q equal to So, we plug everything here. So, C is 2.17, L of the channel is 46 and the discharge is 5000, and then we solve for HE. So, the HE comes out to be 13.6 meter. Hence, corrected design height is a subtraction of HE minus HA, where HA is the velocity of approach. Now, it comes out to be 13.2 meter. Hence, design shall be done for a design head equal to 13.2 meter. Now, design of the crest profile. So, design of the crest profile is a ratio between HA by HE. So, we have the HA as the velocity of approach, and HE is again a combination of HA plus HD, which comes out to be 0.03515, and now we calculate H by HE, which comes out to be 0.58. Since HA by HE lies between 0 to 0.08, it is the value is 0.0315, which is between this. So, and H by HE is 0.58, we can directly use this equation. So, these equations are given in the next slide. So, as we see from the previous slide, that the downstream profile of the low Woogie weir is given based on the H by HE value, and if how much is the ratio of H by HE ranges, and depending upon HA by HE, we change the equation of the Woogie downstream profile. So, we use this kind of equation. So, we plug everything into this equation and we get the value of y reduced to like this. And the position of, now we coming to the position of the downstream apron of the spillway. So, the apron or the toe of the spillway should be at such an elevation that it does not affect the coefficient of discharge. So, this is the coefficient of discharge. Hence, the maximum apron elevation is the TEL, the tail water level, and which is subtracted by design height and the depth. So, which comes out to be 190.41 meter. Hence, provide the toe of the spillway at a level of 190.4 meter. Now, we can calculate the discharge intensity downstream of the spillway piers, which is again a ratio of discharge divided by area. So, area we calculate early. So, this is around 80.7 meter square per second. So, this is the specific discharge. So, the unit is in meter square per second. Now, if d is the width, then the velocity head will be the discharge divided by the depth in meter per second. Now, we calculate the specific energy. Now, we are going for the Stirling basin design. So, we need the specific energy, which is the depth plus the kinetic head. So, d divided v square by 2 g, where we calculate from here v and the 2 g, g is the acceleration due to gravity. But the specific energy of the spillway is 213 meter minus 194.4. So, it comes out to be 23.214. So, we plug everything in the equation of the specific energy. We have given the specific energy as 23.21 and the specific energy using the equation here. So, we can calculate d here. So, it is a quadratic equation, and by we can calculate by trial and error method the quadratic equation, or we can use numerical method or computer programming to solve this kind of equation, and we comes the d value as 4.2 meter. Now, the downstream profile is designed between the relative level 200 meter and the relative apron level 190.4 meter. Hence, the maximum ordinate y is the subtraction between 200 and this 190.4, which comes out to be 9.6 meter. Now, since we are calculating the profile, we plug everything into this equation, which we calculated earlier. So, x comes out to be 15.08. Now, the remaining coordinates of the downstream profile will vary between x and 15.08, which can be worked out in table 2. So, this is the coordinates of the downstream profile here. As you can see, this is the x level, this is the x, the horizontal, and the vertical axis. It is like a projectile. So, once you plug these values here, you get the x value corresponding y value, the related to x value, you will get this one, this curve. So, this is the downstream profile of the coordinates. Now, the coordinates of the upstream profile, it is vary according to this. So, this is listed here. So, this way we can design the complete design spillway. So, thank you.